Hello, I have another review video for you. This time it's writing force equations for forces acting in the x and the y direction. It's another step in the process I call the yellow brick road. It's a skill that we need to be able to become proficient at in order to solve equations involving forces. So let's take a look at the situation that I already have drawn here. I have a block that's sliding across the ground. There's a rope attached to the block, and a person is pulling on the rope so that the rope is exerting 100 newtons of force on the block, and the rope is elevated from the horizontal at an angle of 30 degrees. It is moving at a constant velocity, so this is a free particle. So I'm just going to go ahead and write that down here so that we don't forget that. Now remember, a free particle means that it's not accelerating, and it also means that the forces acting on that block all will add together and give you zero. So the first step I really need to follow here is to draw a force diagram. So I'm going to do that. This will be representing the block. I'll draw the force of gravity straight down, which is the direction it always points at. Now I know that there's a normal force that's acting up. Now I'm drawing it smaller for reasons that you may see in a few minutes. But there's the normal force. Now I've got this pulling force that's off at that angle, so I'm going to label that P. And because the pulling force is pulling to the right, and because I know the block is not accelerating, I know that there must be a force to the left, and that of course is friction. So to continue with this, I want to, these are all the forces that are acting. I want to put a coordinate system on here, so I'm going to go ahead and add my familiar x and y coordinate system. It's a little bit crooked, but I think it'll work. This is the x direction. This is the y direction. And then I'm going to label the angle, which is right here, 30 degrees. So now we see that the pulling force is pulling to the right and pulling up. The normal force is being exerted up. The friction force is being exerted to the left. And the force of gravity, of course, is being exerted straight down. So since the pulling force is not in either just the x or just the y direction, I need to find its components. I'm going to need to use its components in the x and the y direction. So I'm going to draw in the component of the pulling force in the x direction, and I'll call that P sub x. And I'll also draw the component of force in the y direction, P sub y. So now I have my force diagram labeled, and I'm ready to start writing these equations for forces acting in the x and the y directions. Now, if I want to introduce the Greek letter sigma to you, sigma, it looks kind of like a square looking E, sigma. And this is a Greek letter that just pretty much means the sum of. And the sum of whatever comes after sigma, right? So that just means I'm just going to add up whatever I put in there. So I'm looking at the forces in the x direction first, so I would abbreviate that something like this. Sum of forces in the x directions. I'm going to put a little colon there. That's what I'm going to have afterwards. You do not have to write this down all the time. I'm just doing this to make this very clear what it is that I'm writing out. So if I look up here in my force diagram, I see that the normal force, the force of gravity, these are forces that are strictly in the y direction. So I don't need those here. But in the x direction, I see that I have the force of friction is a force in the x direction. And then the component of the pull, P sub x, is in the x direction. So I'm going to just write that out. F plus P sub x. That's adding them together. Now, the actual values may be positive or negative. I'm not going to worry about that right now. I just want to write that in there. And since this block is not accelerating, it's not accelerating in any direction, including the x direction, then the forces acting in the x direction must add up to 0. So those forces equal 0 newtons. And once again, I put that little slash in there just to denote the fact that that's a 0 and not an O, so you don't see that as on. Now if I look in the y direction, I want to sum those forces up, and I see that here I have the normal force, the force of gravity, and then P is pulling up by the amount P sub y. So I would then write the sum of forces in the y direction would be given as N, normal force, plus W, the force of gravity due to the Earth, plus P sub y. And once again, this block is not accelerating, so it's not accelerating in the y direction, so all of those forces must add to 0. Now these are the force equations for the forces acting in the x and the y directions. If I knew, for example, over here what one of these forces was, I could solve for the other one. Here I'm going to need to know what two of them are to solve for the third one, but I can usually find that information. In fact, we can solve this equation right now because, like we showed in the last video, we can find out what P sub x is. If I look up here, I see that P sub x is the adjacent side of this triangle. And what you recall is that the adjacent side, in this case P sub x, is going to equal the force, which is pull, and since it's the adjacent side, it'll be cosine of theta. So I can put this into this equation. F, and P sub x is a force that acts in the positive x direction, so I say plus P cosine theta equals 0 newtons. Well, I know that P is equal to 100 newtons. That's what I said it was earlier. So that's 100 newtons times the cosine of the angle, 30 degrees, and that equals 0 newtons. Now, recall that cosine of 30 degrees was 0.866. So that's F plus 100 newtons times 0.866 equals 0 newtons. That F, so this is 86.6 newtons, equals 0 newtons. And if I solve this for F by subtracting 86.6, I guess I need to go over here. F then equals negative 86.6 newtons. Now, F points in the negative direction, so that makes sense that it should be a negative force, and it's the same magnitude as the component of the pull in the x direction, which makes sense because they're the only two forces acting in the x direction, and they have to add to 0. So, this is how you can write these equations for the forces acting in the x and the y direction. Start with a good diagram. From the diagram, make a force diagram. If you have components, sketch them in, and then you write out those equations for the forces acting along each direction separately. And then if you know some values, you are able to solve them. Hopefully that helps.